On our program, Radar, how it works, its role in air traffic control, and satellite launchings. The origins of radar go back to the late 1800s, when Heinrich Hertz proved that radio waves, electromagnetic waves just like light, could be reflected by metal objects. Soon after, Germany, France, England, and the United States began developing detection systems, which culminated around the 30s in the birth of radar. Radar, an acronym for Radio Detection and Ranging, detects remote objects in space. It will also open the doors of some buildings or switch traffic lights. It is used in ships, aircraft, harbors, and airports. Like a beacon in the dark, radar sends a beam of radioelectric waves out into a portion of space. Radio waves are invisible, but like electromagnetic waves, they travel at the speed of light, 300,000 kilometers per second. Any object in the path of the transmitted beam, such as an airplane, will reflect some of the waves back to the radar. Since the travel time of the waves is known, the distance of the object can be deduced by measuring the interval of time between the initial transmitted signal and the echo. Essentially, a radar system comprises a transmitter, an antenna, and a receiver. The transmitter sends out a stream of short pulses, each a few millionths of a second long. These pulses form what is known as a radio wave train. The wave train is sent toward the antenna through a metal tube called a waveguide. When they emerge from the waveguide, the waves are projected against the antenna's reflector, usually consisting of a metal screen. The reflector reflects and focuses the waves in a beam of varying widths. The shape and size of the antenna determines the fineness of the beam, as well as its range. The larger the antenna, the narrower and more directional the beam, and the longer its range. A rectangular-shaped antenna, which is wider than it is high, transmits a beam that is narrow but broad in height. More often than not, the antenna yaws, turns about a vertical axis to scan space in all directions. For example, some radars used for air traffic control rotate an average of 6 times a minute and give an aircraft's position every 10 seconds. After beaming an impulse out towards space, the radar listens for the reflected echo. It does so for a few thousandths of a second, long enough for the waves to reach a target and come back to the antenna before another impulse is sent out. The reflected echo is picked up by the same antenna that was used to transmit the initial signal. Indeed, a device known as a TR cell, transmit-receive cell, acts as a switch. The TR cell momentarily suppresses the receiver during the brief period of the transmitted pulse, but reactivates it in time to receive any echo pulses. To prevent it from confusing echo and radio waves coming from other radars, the receiver is only sensitive to the frequency of the waves the transmitter sends out. In a first phase, the receiver detects and amplifies the signals received. Because they are very weak, they are 1,000 billion times weaker than the initial signals. In a second phase, the receiver sorts the various echoes that reach it. If the purpose of the radar is to detect aircraft, for instance, the receiver will take out any echoes from stationary targets, such as trees and buildings. It does this by taking advantage of a familiar physical phenomenon called the Doppler effect. We experience this effect when we hear the whistle of a moving train, for example. When the train is moving toward us, the whistle is raised in pitch. Conversely, if it is moving away, the sound is lowered in pitch. The same effect occurs with radio waves. If the object they encounter is an airplane approaching the radar, the reflected waves are in a sense compressed, and their frequency increases. Conversely, if the plane is moving away from the radar, the reflected waves are distended, and their frequency decreases. On the other hand, when the object encountered is stationary, a mountain, for example, the frequency of the echo signal remains the same as the frequency of the emitted pulse. That's how the receiver is able to distinguish moving echo reflected by moving objects from unwanted stationary echo. The Doppler effect also enables the receiver to determine the object's speed by measuring the difference between the frequency of the waves emitted by the radar and that of the waves reflected by the object. The radars used by police to detect cars exceeding the legal speed limits operate on the same principle. Since it knows the direction of the antenna in which the reflected echo is the strongest, as well as the delay time of the echo, the radar has all the data it needs to define the position of a moving object. A calculator processes all of the useful radio waves, compiles them, and translates them into information the radar user can understand. Through fog and in darkness, radar detects objects located miles away. It extends the human eye with hawk-eyed acuity and remarkably long range. Thousands of planes streak across the airspace of the planet continuously. Well, thanks to specialists in international civil aeronautics and to radar systems, passengers and merchandise are able to circulate safely. Every day, whatever the weather conditions, thousands of airplanes all over the world take off, fly to distant destinations, and land without incident. To ensure their safety, these aircraft are continually monitored on the ground and in the air. Air traffic controllers rely on various instruments to do this. In compliance with air traffic control regulations, airplanes use specific airways. These airways, which correspond to well-defined air corridors, are marked out by beacons on the ground. Set up all over the planet, except for the oceans and deserts, these beacons are invaluable navigational aids. One type of beacon is the VHF, very high frequency, omnidirectional range, known as VOR. VOR consists of a series of antennas arranged in the shape of a crown, which continually emit a radio signal in all directions. That signal, picked up by a receiver on board an aircraft, bears the beacon's identification. It also gives the pilot a reading on the aircraft's position by indicating the angle formed by the line joining the aircraft to the beacon on the one hand, and on the other, the line between the plane and north. Another type of beacon, called DME for distance measuring equipment, is generally associated with VOR. DME consists of a vertical antenna, and it indicates to pilots the distance that separates them from the beacon. The plane emits a coded radio signal. When the DME receives it, it retransmits it right away. By measuring the delay time between the transmission of the signal and its return, the receiver on board the plane measures the distance between the beacon and the aircraft. VOR and DME beacons enable pilots to know their exact position in space. They are also displayed on air traffic control screens as small numbered triangles along the air routes. Whenever he flies over a beacon, the pilot notifies the control tower. The controller can then make sure the plane is flying according to the flight plan. In the most modern air traffic control centers, a controller's workstation consists of a very high-definition television screen whose colors can be adjusted to suit the controller's preference. The screen shows in synthetic form the situation of a section of airspace. It displays in the form of small squares aircraft's past and present positions as measured by a group of primary and secondary radars. Primary radars give the range and bearing of aircraft by measuring the interval of time between the transmission of a wave train and the return of the waves reflected by the planes. Often overlying the primary radar is a secondary radar, which consists of a rectangular antenna and which sends out a coded interrogating signal. A transponder placed on board each aircraft receives the interrogating signal and responds with a signal indicating the identity and height of the aircraft. All the information collected by the radars are displayed on the controller's screen in the form of labels attached to each symbol representing an aircraft. They are repeated every 4 to 10 seconds. If he wishes, the controller can also view the data concerning an aircraft's flight plan. He may, for example, want to see the aircraft's future itinerary. He can also check to see at what time the aircraft is due to fly over the next beacon. Air traffic controllers use these detailed images to make sure aircraft maintain a safe distance from each other at all times. The controller must be able to spot any possibility of collision in advance. In this, he is greatly assisted by his computerized workstation, which, in the event of an emergency, will immediately display an alarm signal. An emergency might be any number of situations: the paths of two aircraft converging, a sudden loss of altitude, or even a hijacking. The alarm signal brings the problem to the attention of the controller, who can then tell the pilots how to proceed to rectify the situation. An aircraft remains under surveillance by the control centers up until the moment it lands. For this final stage, the pilot relies on his Instrument Landing System, or ILS. An ILS system consists of broadside antennas. Some of these antennas, at the end of runways, emit a beam in the form of a vertical plane passing through the axis of the runway. Others, running down both sides of the airstrip close to where the wheels touch down, beam in a sloping plane of about 3 degrees. The intersection of the two plane beams determines the aircraft's ideal descent path. Receivers on the aircraft indicate to the pilot what the gap is between the real position of his aircraft and the ideal position required. Air traffic control techniques are constantly improving. The day may not be far off when satellites transmit the positions of aircraft directly to ground computers. One of the latest satellite imaging techniques uses radar. And whenever a radar device is put into orbit, the launcher rocket's trajectory is monitored by another radar system. What would we do without these devices? Satellite launching and aerial mapping are areas in which radar plays a crucial role. Some radars, called trajectography radars, can, with exquisite precision, track a rocket's path as it is launched into the sky. Used when satellites are put into orbit, these radars are equipped with an enormous parabolic antenna, or dish, which emits a very fine beam of radio waves. Calculators at the launch center keep the trajectography radars continually abreast of the rocket's planned trajectory. The radars can then focus their beams on the rocket in order to track its every movement. Trajectography radars can measure the rocket's position continually and accurately, within a few meters for range, and a few hundreds of degrees for bearing. They are able to do this by acting as a primary or a secondary radar. As a primary radar, they transmit a wave train that is passively reflected off the rocket. As a secondary radar, they transmit an interrogating signal to which a device on board the rocket responds. The information furnished by the trajectography radar can be viewed on a television screen. It allows the controller to ensure that the rocket has not veered off course and remains inside its assigned safety lane. The safety lane is the airspace in which the rocket can proceed without its destruction posing a threat to the people on the ground. Should the trajectography radar detect an abnormal trajectory, the controller can then attempt to correct it. As a last resort, he may have to order the rocket destroyed. The range of a trajectography radar is approximately 5,000 kilometers. That range will determine such parameters as the velocity, bearing, and altitude of a satellite at the critical moment of reaching its orbit. Trajectography radars are used to control the launching and orbiting of satellites. Some observation satellites are equipped with another type of radar, a synthetic aperture radar, or SAR. This radar is an airborne ground mapping system consisting of images based upon the interpretation of microwave beams. As the satellite orbits, the radar's antenna sends out a wave beam in the form of pulses toward the ground. The waves are reflected by every point of the ground surface. The antenna picks up the echo. The echo can be synthesized into a detailed ground map. Interpreting the radar picture alone, however, can be tricky. A radar image will therefore often be compared to a color optical image. In a radar image, the luminosity of a given point is proportional to the intensity of the echo. The corresponding ground area reflects back to the radar. The intensity of echo depends on such physical surface properties as inclination and rugosity. Micro-reliefs, river embankments for instance, strengthen the reflection of waves to the radar. Radar images can also help to clearly make out a deforestation front in a heavily wooded region. A radar image of calm water, however, appears as a black surface. When calm, water behaves like a mirror. It reflects the wave beam transmitted by the radar in a direction opposite to that of its impact. So the reflected waves do not go back to the radar. Conversely, the waves produce various reflections that amplify the echo toward the radar. In a radar image, a turbulent sea, for instance, will show up quite light. An oil spill is therefore easy to detect, even in stormy waters. No matter how thin it may be, it will reflect the radar wave in a direction opposite to that of the radar. A dark spot in the middle of a light-colored expanse, the oil slick patch stands out very clearly in the radar picture. The synthetic aperture radar provides an image resolution of about 30 meters on the ground. Moreover, it will reveal in remarkable detail certain metal structures, such as railroad tracks or boats, which are actually very small and invisible in optical imagery. These structures show up clearly in the radar image because metal is an excellent reflector, which sends a powerful echo back to the radar. Synthetic aperture radar can collect images night and day, whatever the cloud cover. Because of the particular precision of the images it furnishes, satellite-borne synthetic aperture radar is the instrument par excellence to keep close watch over our planet. In 1981, thanks to its onboard radar, the Columbia Space Shuttle discovered a network of waterways millions of years old. This hydrographic network is hidden in the most unlikely place, beneath the sands of the Sahara Desert.